Hello, everybody, and welcome to episode 109 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike, and that is Gavin. And Gavin, it's been a little bit.
It sure has. For the listeners, it's been the normal 2 weeks, but for us, it's been, I think, a full month.
Something like that. Like, I thought we'd stop the podcast for something and just never talk about it. But no, as it turns out.
Yeah, so we, recorded our section of last episode. So if you haven't listened to last episode, we had a guest, and we recorded part A, sort of just me, Mike, and Fia, like a month ago. And then just due to some scheduling things with the guest for the second part of that episode, we had to delay the episode by a week. So I think it's been at least 3, if not 4 weeks, probably 4 weeks since we've actually recorded together, or really even spoken for that matter. So how's life, buddy?
Things going pretty great.
Oh yeah, we should also make a quick mention. Fia is occupied by grad school things. It's her last semester of grad school, so she's finishing up all of her good science. So she could not join us for this week, which will become relevant in a little bit.
It will. As far as I'm concerned, you mentioned school before. I would say one of the best parts about being a teacher is that I have the week off. And
what? Why?
Spring break.
Oh, that is this week.
It is.
Wait, interesting.
Fantastic.
So my birthday is in, give or take, actually exactly 2 weeks from when we're recording this. And spring break was always over my birthday, which was always a bummer because all of my friends would leave on spring break. And I never got to, I think I had like 2 birthdays growing up that I got to spend with like my friends from school.
I think that it is not like a formal policy, but in general, they try and like coordinate it to Easter. So that way you can just like lump in Good Friday with spring break and, not have to, worry about anything else. And so
which is funny because my university, yeah, it is. My university gets neither Good Friday nor the Monday after Easter off. So
really?
Yep.
Yeah. I mean, like, universities tend not to worry about that. So I know when I was at SU, we got Labor Day and Martin Luther King Day off, and that was it in terms of holidays.
Interesting. Maybe because I went to a state school for undergrad, it was a little different.
That's entirely possible. But either way,
and then grad school is just a black hole, thanks COVID. So I don't remember almost any of what we had off in South Dakota. Anyway, we've rambled a little bit.
Yes, we are here right now. So Gavin, I have no idea what the typical spiel is at the beginning, but do you want to go ahead and tell the people what they need to do in terms of the podcast?
Absolutely. So firstly, since I mentioned we are doing something a little different with the topic, and since you probably already saw it when you clicked on this episode, last episode I said we're going to be talking about cephalopods, the group of mollusks that includes squids, octopus, cuttlefish, etc. But I feel like it would be a crime to do a marine invertebrate episode without Fia here. So I decided on a last minute change to something from a couple episodes ago. And I didn't look up which episode that I mentioned this in because it really was just an offhanded comment. I mentioned that the time, like the number of hours in a day has not always been the same throughout Earth's history. And Mike was like, can you tell me more about that? And I was like, no, I cannot. But now I can. I've learned. So that's what we're going to be talking about today. But in terms of housekeeping things, do not forget to rate the show on whatever platform you listen to us on, as well as to follow us on our various social medias, Twitter, while that's still around, Facebook, and YouTube, as well as to give us any feedback on the show and suggest any future topics you'd like to hear on the podcast. If you want to be a guest on the show or to suggest a topic, we have Google Forms down below in the show notes that you can fill out, which would be immensely helpful for us. And next episode, given that it's an episode that ends in 0, is a Mike Takes the Wheel episode. And I know that I already know the answer to this, but Mike, do you know what we're doing next episode?
I don't have a clue. Again, just to remind everybody, I thought there was a small chance the podcast had just been canceled and we were never going to speak of it again. Because it had felt like it had been so long since we had recorded
Yeah,
or discussing. So no, I have no idea what we're going to discuss. It's going to be something weird. I'm sure they'll have a wild story as to how I got there, as
love it.
is customary at this point. And it'll be interesting. That's all I really got for you on that front.
Yeah, we wouldn't expect anything else, buddy.
I appreciate that.
Hello, just a quick interruption here to mention something that I meant to mention, but then forgot when we actually recorded the episode. So, if you remember, a little while ago, I actually produced a video for the Paleocast Gaming Network about cool paleontology aspects in Pokemon. I actually have just put out another video for the Paleocast Gaming Network, this time talking about how new species of Pokemon happen. And it's strikingly similar to how it happens in the real world, and it's all actual lore from within the games. So there'll be a link to that down below. Please give that a watch. It will make me feel good about myself, and let me know what you think. And now back to the episode. But with that, I guess a little potentially a preview for next episode. What is our today in history?
So today in history comes from, so we got April 5th in history, comes from 1997.
Okay.
This lasted a little while. Gavin, what were some TV shows you watched as a kid?
Oh God. Can you give me a hint? Like, was it a cartoon?
Not a cartoon.
Okay. Friends?
Not Friends. More serious.
More Sopranos?
Not Sopranos. I'll give you a little bit more of a hint here. Not like a scripted show. Something you would see on like I don't know, like
Cops?
Discovery or Animal Planet or something.
Oh,
not Cops.
Shark Week?
Not Shark Week.
The Most Extreme?
Not The Most Extreme. I'll give you one more
I got
guess.
nothing then, buddy. One more? Okay. The Crocodile Hunter?
In 1997,
No
Steve
way.
Irwin's The Crocodile Hunter debuted on April 5th.
That's killer.
Too soon.
Oh no.
Too soon.
I didn't mean it. I didn't know.
Too soon.
I'm sorry, Steve. I didn't mean it.
Man, what an absolute legend. And I love the fact that Steve Irwin's kids are just like, they have the same enthusiasm.
Awesome. Yeah.
Yes, it is. They seem rather fantastic. And Steve Irwin was a light to this planet.
He sure was. But I think it's an inspirational thing that like he went out doing exactly what he loved. Like if you were to ask him, I'm sure like in the premiere of The Crocodile Hunter, if you're going to die, what would you like to be doing when that happens? He'd just be like, oh, trying to get an animal to show people. And that's exactly how it happened. So
that's honestly probably exactly what he would have said, and he would have said it with a smile on his face.
And an accent that I love. I'm sure, and maybe this is just some deep psychological stuff. I really enjoy Australian accents. I think 100%. They're just very fun to listen to, and I'm sure he is the reason why.
That's actually probably a good call because I've always loved an Australian accent, and I never thought much about it. But I think you're 100% right. It's probably got quite a bit to do with him.
Yeah. Awesome. Well, thank you for that, buddy.
And thank you to Steve Irwin for existing.
Yeah.
And now that we have that out of the way, Gavin, so time, does it exist?
Sort of.
All right, that's about what I expect.
We're going to be doing some math and a little bit of physics in this episode. Don't worry, don't click off. It's not going to be that hard, I promise. So, Mike, off the top of your head, how many hours are there in a day?
So, like the default answer is 24.
Right.
Isn't it? I'm trying to remember here if like the technical like time it takes the Earth to spin around the sun, if it's just over or just under 24 hours. But then you also run into the question of how do you measure that? So I'm going to stick with 24 hours and go and be comfortably wrong, but close enough.
Well, it's funny that you said the time that it takes Earth to move around the sun, because that's a year, not a day.
But the you know what I'm trying to say, though.
That the Earth spins. And we'll talk about a little definitions here in a second. But
yes,
a day technically is 23 hours, 56 minutes, and 4 seconds.
Right, okay.
Which is technically 23.934 hours. So for all intensive purposes, it's 24 hours. But when we talk about large timescales and things like that, that small difference can eventually turn into a big deal. So we'll come back to numbers in a little bit. But I think it's actually a good segue. Thanks for that you confused a day and a year.
Really?
Because
Is that what we're accusing me of?
Yep, sure am.
All right, fine.
So, I'm sure most people, including Mike, I am giving you credit for this one, do know the difference between a day and a year. So, a day is the amount of time it takes for Earth to rotate on its axis. So, if you had a globe, if you were to just spin it on its axis once, that is a day. A year is the amount of time it takes for Earth to revolve around the sun. So it's full orbit. And that also is, we also always abbreviate that as 365 days. Again, technically not quite right. It is 365.25 days, which is why we have leap year every 4 years. So it's that extra day every 4 years sort of makes up for that.
And that's why we have it.
Right.
There's also a weird thing. I do know this.
Yeah.
Where it's every 100 years there isn't a leap day, except for every 400 years, just to try and get it in as exact as possible.
Interesting. I didn't know that actually.
Yeah, it's a weird because I knew that partially because of length of presidential terms. Like Bill Clinton's term was slightly longer than William McKinley's would have been had he not gotten shot.
Right.
Like a loser.
But yeah, so that is sort of some of the numbers we're talking about here. Slightly less than 24 hours for a day, and then slightly more than 365 days for a year. And as you might have guessed, since we're talking about it on this here particular podcast, which is mostly about paleontology, this has not always been the case. Earth, in its past, used to spin faster. Not around the sun. That has mostly stayed the same. But rotated. So if you were to just spin the globe really, really fast, that change in speed is what we're talking about here. And because the length of a day shortens or changes, that means the number of days in a year changes, if that makes sense.
Mm-hmm.
And they're altogether, there are lots of forces. So if you were to ever take a more advanced physics class, which, in my defense, I have not, so take this with a grain of salt. I only took the basic 2 semesters of physics. So gravity is something that's basically affecting everything all the time. So it's, even small things have a technical effect, or really far away things have a technical, gravitational effect. But for the most part, it's too small to measure. But when we're talking about some objects in space, little tiny effects can become a little bit bigger. So we're going to have to think on big scales and long time scales here in this episode.
How big and how long?
I should have seen that coming.
That was actually a serious question that I got midway through. And I was like,
So long time scales is in basically the entire history of the Earth. So we're only going to be mentioning, give or take, 550 million years or so, just because those are the time periods that I'm familiar with. But hypothetically, you could take this all the way back to the beginning of the Earth, around, over 4 billion years ago. And we're also going to be talking about days and years and, like I said, a little tiny bit of math. So I mentioned before that Earth used to spin faster, which would mean that days were shorter. Does that logic kind of make sense?
The Earth spins faster, so it's going to complete one revolution faster.
One rotation.
One rotation faster, and as a result, those can just be days are going to be faster. The time it takes to go from midnight to midnight will be shorter. Yes, that makes sense.
Okay. Cool. And so over time, Earth spin has been slowing down. And why might that be? You'd think everything in space, for example, if you were to, shoot a gun or throw a baseball in space, the laws of, Newton's laws of physics state that should just go indefinitely until it hits something. But why isn't that necessarily the case for the spin?
Is there my default answer is friction. Space complicates that, but any other guess? So I'm going with friction.
You're absolutely right, but it's not on something you might think. It's the Earth's friction on itself, sort of.
Okay, that's people normally have to pay money for that kind of thing, but tell me more.
So, a little background. I'll explain it first in that the moon is stealing our spin from us in order to escape from Earth's gravity.
The moon is stealing. Okay.
So the moon gets slightly farther away every year, all the time. It's getting ever so slightly farther away from Earth. There is no such thing as like a perfect orbit. Eventually, the moon would come crashing into the Earth, or it will escape. Those two things are inevitable. But the way that the math...
Entropy, yada.
Right, exactly. And so the moon is using its... using physics to escape from us. And how it's doing that, for complex physics reasons, basically, the way the moon moves the tides... Because if you didn't know, the moon is what causes tides on the ocean.
Yeah, Bill O'Reilly.
Is he a flat earther?
He's not a flat. There's a wonderful interview back when he was still on the air with him arguing with some atheist, and he was just like, tides go in, tides go out. You can't explain that. And the dude gives him the craziest look, like you are about to.
You can
react. As it turns out, yes, we do know what causes that.
Wow, that's really funny.
Yes, go look it up for anybody that hasn't seen it.
Yeah, absolutely. So, the moon spinning around the Earth, or revolving around the Earth, is what causes tides. Basically, the side that is, toward the moon of the Earth, and the side opposite that, the oceans kind of bulge at those spots. And so the parts that the moon is not at, that's when you have low tides. And basically, Earth spins faster than the moon revolves around the Earth, which is why a lunar cycle is 28 days, but a day is just a day. And so that sort of mismatch causes the Earth's ocean to basically ever so slightly slow down the spin of the Earth. Like I said, lots of really complex physics going on there that I don't understand, but I trust the people that I read it from, which is NASA. NASA has this in several places on their website.
And why do you trust NASA?
Well, they've, to my knowledge, never lied to us before. I'm sure Bill O'Reilly might have some objections to that.
All right, but so we're going to trust NASA on this one. I think I could live with that.
Yeah. And so, based on our understanding of how this Earth-Moon tide system works, again, based purely on math, and for a long time, this is math that has been known for a while, that for every 100 years, we gain roughly 0.0024 seconds to our day.
Over how many years?
100.
So that is functionally unnoticeable.
Yes, totally.
It sounds difficult to measure even. Like, it sounds like this is a math thing more than something that can even be measured.
Exactly. And that's kind of the point for this next whole section of the episode here, is that the next bit that we're going to talk about is all just based on math and what the physics says should be happening. And just sort of it's hard to put that small of a time in perspective. What that roughly works out to is each day gets 1 second longer every 42,000 years or so.
Yeah, it's a long time.
Right, not noticeable at all.
And that wouldn't
Um,
even, like you mentioned before, that wouldn't even, push it to like, 24 hours and 1 second. Like it would actually push us closer to being exactly at 24 hours long.
right. And so that sounds like a really small change, but when we're talking about the history of the Earth, we have thousands of years to spare. There's been thousands of years, thousands of times over. So, over time, that really, really adds up. And so, based on, again, all of this just pure math, this is not making any paleontological observations like from the rocks and things that tell us anything that this should be happening. This is purely based on physics. Based on this math, when the non-bird dinosaurs went extinct, so this was 66 million years ago, days were 23 and a half hours long. So even that long period of time, days were only still half an hour shorter.
Which is, noticeable, obviously, but like, not that noticeable over such a long time.
You'd be surprised because, like I said, the length of the sun or the Earth making its trip around the sun doesn't change, which
Mm-hmm.
means that extra half hour adds a couple of extra days to the year. Back at
Okay.
this time, there were 372 days per year.
Huh.
Yeah.
370.
So it was
Yeah,
about
I
a
mean,
week longer.
oh wait, I'm just wondering how that would affect, because like right now I know like a lot of banks and stuff have kind of coasted on the fact that we are close enough to being 360 days, which is a very
hmm
nice number for division and whatnot, and we kind of ignore the other 5 days for those purposes. But at some point, you
Right.
add on just enough days where it becomes impractical to do that,
Right. Yeah, absolutely.
and it just
And
makes you
as
think
we'll
like,
talk, as we'll
yeah.
talk about, 66 million years is not that long of a time.
It's wild to hear you say stuff like that.
Right. And so just to go even further back, when complex animal life first became widespread in the Cambrian period, which we've had an entire episode about, I didn't actually see this anywhere when I was doing the research for that episode, and this was probably over a year ago now at this point. I didn't come across this anywhere. So I literally just like whipped out a calculator and did the math based on how many seconds we add per 1,000 years or however the math ended up working. And so this was 540 million years ago. And that same math works out to just over 20 hours a day, 20.3, which for sure would be noticeable.
20 hours a day?
Yes, 20.3.
Okay. Yeah.
And that means the year would be just over 430 days.
That would cause some problems.
It sure would.
And I mean, like, obviously, like,
It being 360-ish is very convenient because circles are easy to do math on.
Yes. And, like, obviously, no, it wouldn't, because if, like, we just existed with that, that would be normal
Right.
for us. But just, like,
Right, yeah.
an immediate change is obviously what we're talking about.
Right. And I do want to make a quick asterisk here in that, again, this is purely based on math. And over time, because of the way gravity works, so it's, closer things have a stronger gravitational pull on things. That's why, like, if you were to stand on a scale with the moon directly overhead, you would weigh slightly less. But like if there's some, star billions of miles away, technically it is exerting gravity on you,
Mm-hmm.
but that wouldn't change the weight on a scale at all, just because the moon is much closer.
Right.
And so back when the moon was closer, because like I said, it is ever so slowly slipping away from us. When it was closer, that means that it would be stealing our spin more quickly. So it's like this isn't a completely straight line the way the math works, but it's sort of like, did you ever take like an intro physics class?
I did, yes.
So you know how you basically just ignore wind resistance for everything?
Yep.
That's what we're doing here.
Understood. Okay.
Yeah, because so if any of our listeners have not taken intro physics, so if you were to just do the math on like throwing a ball or shooting a ball out of a cannon or something, in intro physics you ignore the wind resistance because that makes the math very complicated, and that's what we're doing here. So
yeah, we're anything to make things a little bit easier, both for you and I, as well as for the listeners. We're generally going to take that option.
right, and so this entire last bit has been purely math, and I've said that several times because I want to make that clear. Just math. But, your math is fun if you're a nerd. But what does this actually mean for paleontology? Why are we talking about it here on this podcast? So we can actually try to find evidence that this was the case in fossils from these different time periods. And so if we bring back those numbers from the Cretaceous period, that 66 million years ago, just as a little refresher, we said that at that time, the math says days should be 23 and a half hours long and that there were 372 days a year. Keep those two numbers in your brain.
Which two numbers? 372 days a year and
23 and a half hours in a day.
Understood.
Back in 2020, so not that long ago,
right,
a paper was published on a particularly well-preserved specimen of a bivalve, so inadvertently, sad that Fee is not here. So this is a bivalve called Toriides sanchezi, which is a type of bivalve called a rudist that were major reef builders at this time period in Earth's history. So corals and stuff were still around, but at this particular time, bivalves were the ones building reefs, similar to like oysters and stuff today. And this species had photosynthetic algae that it lived with, like corals do today. And because of this, they sort of operated on a day-night cycle. They would add layers to their shells during the day when they were productive and when their photosynthetic symbiotes were happy and doing their thing. And then they would stop adding layers to their shell at night. Think of this sort of like tree rings.
This is but like instead of being every year, it's every day night?
Yep, they add just a little bit every day and then stop adding it at night. So you can see, like a tree ring, how they have the light patches and then the dark patches. Think of that as we're talking about this here.
Damn.
And so they would do this every single day. And you can sort of tell very small but noticeable chemical changes based on the seasons. In the rainy season, they'd have more of a particular element because more runoff comes from the land out into the oceans. And then during the drier season, they would have less of that, just as a simple example. And what these scientists did is they analyzed each of these little bands in this particular specimen and basically tried to figure out how many bands were there in a year once they get to that same repeating sort of quantities of those different chemicals in their shell based on the seasons.
Right.
And wouldn't you know it? It matches up exactly. There were 372 cycling layers in this little guy's shell.
That's incredible.
Yep.
I mean, it's almost the same thing when you've got all the math and predictions and everything. We mentioned NASA before, for them to send a rocket to Mars and it's going to land on this 3 square foot area, and they get it correct. It is.
Yeah.
It is just absolutely nuts how when people are really good at their job and they're really smart and they're able to do all this, and then it gets proven out, empirically, not just with math, but in the real world. It's incredible.
Absolutely. Although all that wonderful, well-deserved praise aside, because they make their shell this way, hypothetically, we could do this with anything that does photosynthesis like this, specifically corals. And so we have corals. Corals are a really, really old group of animals that we have lots and lots of fossils of. And so people have tried to do this with corals as well. And this is where I had to have that disclaimer earlier where it's like the math isn't perfect because we are ignoring some of the ways that gravity works.
Okay.
So we did the math earlier for the Cambrian period, and that was 20.3 hours in a day and 430 days in a year. We don't have corals quite that old that have been measured in this way, but we have corals from a little after that show 420 days in a year.
Nice.
Nice. So that is about 440 million years ago. So it's like, 100 million years, and you take away 10 days off of the year. Based on the math, that's close. It's not as correct like it was with the Cretaceous, but it's close.
You expect the errors to increase the further back you go.
Exactly. And that's also the case with like the, chemical isotope measurements that they were taking on these things. It's like as the further back in time you get, the less reliable the data becomes, just because there's less of it, there's more time for it to degrade, and also just the way gravity works and well, just math in general works, error builds up over time on itself. So,
right.
So it's the math on that is close, and then also similar to a little after that, from 380 million years, we have some corals that suggest 410 days, which is also close to the math, but not quite.
Close enough.
Close enough for my book, though. Close enough for government work, as they say.
Absolutely. Now, has this been? Do we see any kind of similar? Right, maybe seeing is actually the wrong word. Does the math work out that any other planets that also have moons, should experience similar kinds of slowdowns in their rotations?
Wonderful question. I didn't actually find anything about that, but just off of my knowledge of our other planets, I would say probably not, at least for the rocky planets, because none of them have water, which is what's doing the work.
Okay.
The gas giants, potentially, because all of that, I would assume, well, actually no, because they each have a bunch of moons.
Right,
and none of them are as close in size as our moon is to the Earth. They're all very small relative to their planet.
Proportionally. And
because they're each like all moving around in different ways, I would imagine that that's just a lot of noise that I'm sure it doesn't fully cancel each other out, but probably like some of them cancel some other ones out. So it's not working quite the same.
Again, like it probably does happen theoretically, but even to measure it mathematically would be, incredibly difficult.
Right, and I'm sure people have. I'm sure that has been a question that has been asked.
Right. I'm probably not the first guy.
Right. But I actually don't know. I'm going to make a note of that because I have a friend here at my university who is in our astronomy department.
Mm-hmm.
I'm going to make a note of that. I'm going to ask her.
Yeah, please do.
Yeah, so I will, hopefully, assuming my memory holds up, report back on that next episode. But in the meantime, I will have some links if you want to read more about this in a much more articulative way than I just have talked about it. There'll be some links down below. As well as a neat sort of GIF or GIF if you're a degenerate who pronounces it that way.
You said wrong.
From NASA, sort of just showing the spin of the Earth relative to the moon's, orbiting the Earth. And you can sort of see just that mismatch in time is sort of what is the culprit here. It's a lot easier to visualize than it is to just listen to and understand. So there'll be some cool resources down below, as well as the actual paper from that one bivalve that matched up perfectly from the Cretaceous. So the link to that will be down below in the show notes. And this was just sort of a quick impromptu episode that I threw together once we knew that Fia wasn't going to be here with us.
And thank you very much for doing so. And this has been episode 109 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike. That is Gavin. We hope to have Fia back on the next episode, and we will see you then.
This episode of I Wish You Were Dead was written by Gavin Davidson and hosted by Gavin Davidson, Mike Bryson, and Fenella Campanino. It was sound edited and edited for YouTube by Gavin Davidson. Special thanks to former guests of the pod and to listeners like you.